Coussy and Henry Breeds, who will be presenting on an industry-oriented method to measure wake steering benefits in offshore wind farms.
Let me share my screen.
Okay, let's go. So yeah, first of all, thanks so much for the opportunity for us to present here. So as mentioned, yeah, myself and Juliette, we're from Siemens Energy. We're specifically from our product, our wake steering product for wind farm flow control, which is called Wake Adapt, where we've been actively developing and then also selling this product for a few years. I'm the project manager for Wake Adapt, and Juliette is our solution owner for Wake Adapt. So the majority, actually all of the presentation will be presented by Juliette. She has all the technical information. And what we brought today is, yeah, a little bit different than just standard wind farm flow control. Its title is an industry-oriented method to measure wake steering benefit in offshore wind farms. So obviously wind farm flow control is one thing, but when it comes to using it in industry, you actually need to know how much energy is being produced by wind farm flow control. And that's something that turns out to be quite a tricky topic. And we've spent quite a few years developing methods and also improving methods for proving the benefit from wind farm flow control. I think there's a good saying that in God we trust and all other must provide data. So generally, everyone here is developing really good methods for wind farm flow control, but proving it works and how much is the gain is the key that we're showing here, because there's some specific difficulties with wind farm flow control methods versus traditional power improvement methods, which is focused and proven on the turbine level. And Juliette's going to walk us through those today. So Juliette, please take it away and give the presentation.
Thanks. Yes, so I will present the current, sorry, I need to, yes. So I will first give you some introduction to our product Wake Adapt, then the method we have implemented to measure and validate the Wake Adapt gain, and then all the analysis that we have done to assess the uncertainty corresponding to this process. Then I will present you some of the improvement or the analysis that has been conducted to improve or lower down the uncertainty of the measured gain, and then provide you some conclusions. So first of all, if you don't know, Siemens Gamesa has recently developed a wake steering wind farm control strategy that optimized the wind farm power output. And during of the process, so before the full installation, we can do a swap test or toggle experiment that is attending to validate the Wake Adapt gain. And we have conducted several swap tests in different wind farms, mainly in offshore, but we have tested several size of wind farm, localization, turbine type, and we have also matured the process to evaluate the power gain of Wake Adapt. But it is to be noted that at the end, the aim of the swap test is to not validate only the gain during this swap test, but it's really to have the validation of the gain during the long term of the wind farm lifetime. And since this is applied to every wind farm that we want to sell Wake Adapt, we only require to use some SCADA data, so without any external measurement, and the duration of the test should be approximately 1 year. So it's a bit the, let's say, industrial constraint that is making the topic even more difficult. So I will go through the, let's say, official or latest method to measure the Wake Adapt gain. So then you have an idea of the full process and all the, let's say, assumption that we had to take. So as I said, we are running a swap test between Wake Adapt on and off. So between off, it means that we are not running any wake steering features. And when we are running on, we are activating Wake Adapt, so applying some yaw offsets. And we are switching between on and off in regular intervals. And we are switching for the entire wind farm at the same time. Of course, we are discarding some period at the beginning of the new mode, so between on and off or off and on, to account for wake effects to travel to the nearest downstream turbines. So then we will have those, let's say, those two modes during the dataset, wake adapt on and wake adapt off. And that will be two huge dataset of samples. But then to make sure that we have some quality measurement, we will, of course, filter those datasets. So then we will ensure that the turbine itself is in operation, not curtailed, and so on. But we mainly want to ensure that we have similar operating conditions in the row in the wind park. So we are also filtering or ensuring that all the upstream turbines are as well in operation. And the aim is to ensure that we can compare wake adapt on and off because we do have a similar condition upstream. Then once that we have those two datasets that are filtered, we need to bin the sample into those huge matrices. So for each turbine, we will define, depending on the wind direction, a reference turbines. So you have a plot on the bottom left, where you can see, depending on the wind direction, which turbine we have selected. And you can see that the reference turbine is always free stream, because we want to have an accurate reference wind speed and a reference wind directions. And we use those super reference turbines or those reference conditions to bin the 10-minute samples inside the 2D matrix that will be depending on the wind direction and the wind speed. We have recently introduced some super reference turbines to account for even more accurate reference wind speeds, in the sense that if the reference turbine is not applying some yaw offset, then there is not, we are reducing the uncertainty for the reference wind speed because we are not applying any yaw offset. So at the moment, we are preferring to use those super reference turbines to bin the data, especially for the wind speed. So we will, among those reference turbines, define some super reference turbine where the yaw offset has been removed. Then once that we have those 3D matrices as function of turbine, wind direction, and wind speed, we want to ensure that whatever power gain or power differences is only due to wake adapt operations. Of course, we have samples for wind speed and wind direction where we do not apply wake adapt, so where we are not applying any yaw offset. So for that, we are removing the power differences whenever we don't have any upstream turbine that apply yaw offset. So whenever we don't have any yaw offset, we will put 0 as power differences for those bins. So then that will help us to reduce the variability or the noise in those bins that are not introducing any differences due to wake adapt operation. So basically that will remove the power differences outside of the wake adapt wind speed and outside of the main wind direction where we do have some high wake interactions. So once that we have those matrix bin where we have filtered out only focusing on relevant bins, then we simply do the average per turbine and per bin of reference conditions. So then we have one value per turbine and wind conditions and per mode. And then the goal is to compare wake adapt on and off. So then we have the measured gain. But then since we have only collected a subset of bins over the full wind directions or the full wind speeds, at the end, the goal is to compare the estimation from the simulations. So we will simply do the ratio of the measured gain to the estimated gain, but only where we have collected bins. So the estimated gain is not the full AEP gain, it's only the power differences or the gain where we have enough sample. And this ratio is basically corresponding to the efficiency of the wake adapt. So if this is 1, we have completely validated the wake adapt performance. But then the question is, what is the uncertainty of this corresponding measured gain? And usually we use data where we actually have some wind farm control applied during these datasets. So it's a bit difficult to really assess evaluate the uncertainty of the process. So in order to disregard the impact of the wind farm control strategy, what we have done is to look at several wind farms, always offshore, but for multiple years. And in those data sets, we will apply north calibration to ensure that we can calibrate the wind direction. But then what we will do is we will emulate artificially wake adapt swap mode. So we will pretend that wake adapt is on and off regularly, and then we will apply the process that I have just presented to you. And then the goal is to see how much of the measured gain has been calculated with this method. And then since in this dataset we actually have not applied any offset, if the method is perfect, we will have 0% of measured gain. So this is the method that we have put in place to calculate the uncertainty of the measured gain of wake adapt, or of this method. And before I talk about the unaffected by wake adapt filter, and in this case, since we don't have any offsets, we will just disregard the bins where we don't expect any gain based on the lookup table. So this is the result for one example of an offshore wind farm. So you can see on the top right the data collected over the wind speed and the wind directions. And this is the percentage of turbine where we have collected samples. So in most of the wind speed of interest and wind direction, we have almost 100%. So we have a good coverage of bin because we have several years. So just to present you that we are not relying on only a few months. And then what is the most important is those two figures where you have the benefit as function of wind direction or the benefit as function of wind speed. And then you have 3 lines. The first one is the blue one, is the measured benefit using the SCADA measurement data. And this one should be completely 0 since we are not applying any wake adapt strategy. But then you can compare to the estimated benefit if we would have applied wake adapt. So in red, it corresponds to the estimated benefit or simulated gain only in the bins where we have collected some sample. And the black one is just the estimated benefit, but if we have all bins covered, so basically the maximum benefit available. And you can see that the uncertainty is quite high. In some certain wind conditions, the uncertainty of the measured gain is at the same order of magnitude. So it doesn't happen at all the wind direction of or wind speed. But this is definitely some issue that we would like to reduce. So this is a very general view of the uncertainty for wake adapt for this method, but we wanted to deep dive on why do we have those kind of high fluctuation or high uncertainty. So, and especially why it is more difficult than a simple power curve. So if you go back to this line, blue line, you can see that you have a lot of positive and negative. And if you sum up the line to have the final AEP gain, you can be very close to 0 by luck. But what we are also interesting is the fluctuation or the variation of this measured benefit. So what we have looked into is the standard deviation of those 2D matrix to ensure that we can decrease this standard deviation. And then the other degree of freedom that we have introduced is that at the moment we are emulating a wake adapt mode but we can decide when we are turning wake adapt on or off. So what we also wanted to see is what is the flexibility or the sensitivity to the starting case. So if we start wake adapt on to the first or second sample or third sample, so we have done all the possible configurations and then evaluate the different measured benefit and standard deviation for those different cases. So that's why you have a distribution for all the cases, and 1 point corresponds to one starting case. And then here is the overview of the measured benefits, so the same as before, but what if I only consider the free stream turbines? So that will be the first two, and you can see that the measured benefit is quite small, but the measured benefits significantly increase if I account for the first two rings of the first three rings of turbines. And it's just showing that having this method to only validate the measured gain at the free stream turbines, that is the uncertainty is small enough, but if we really want to have it at the wind farm level, the uncertainty increased too much. And you can also see it when looking at the standard deviation. So we clearly have a higher standard deviations, therefore a higher uncertainty if we account for the full wind farm compared to if we only account for the first two turbines. Yes. And previously, I have only showed one example, but I just wanted to show you another example for another wind farm. So the order of magnitude that are different. So especially when we are looking at the comparison between the measured benefit and the estimated benefit. But the trend or the main conclusion are the same, meaning that the measured benefit is increasing when we are taking more turbine into account, and the standard deviation across the non-affected by wake adapt pins increase when we are increasing the length of the turbine rows. Yes. And then I will just show you some investigation that we have conducted to try to reduce this uncertainty. And I hope I will explain you a bit the blocking point of this method, so the drawback of this method. So the first item is really about the swap period and the swap pattern that we are currently applying into this swap test. Then the second one is about how we are calculating the mean power for each pin and what probability we are currently using. And the last one is about the reference conditions. So how we are selecting those super reference turbines and how do we account for flow propagations. So the first test, so you have 4 different wind farms where we have looked at those 2 metrics. So the measured gain for different starting cases. So again, that's why you have some distribution, and the standard deviation across the 2D matrix. And you can see 3 different periods and 3 different patterns. And of course, depending on the wind farm, we have different trend. But what I wanted to show here is that there is no obvious better swap period or swap pattern. So it's, even if for some cases we could see, okay, I don't know, the second swap period is improving the viability of the measured benefit or the standard deviation, it's not necessarily the case for all the wind farms. So it's also a bit the complexity at the moment is that we need to ensure that whatever improvement or mitigation action we are finding, it needs to be generalized to different wind conditions or different wind farms. But this one didn't really help to reduce the uncertainty. Another one that improved the uncertainty is how we calculate the average power in each in each bin of the 2D matrix, depending on the wind speed and the wind directions. So at the beginning, we only did the average, simple average. But the issue is that we are not ensuring that we have the same wind speed distribution in baseline and wake adapt mode. So we could have some positive or negative differences just because in that specific bin, we have collected some lower wind speed or some higher wind speed. So the scaling the power, the first method that I called scaling the power is just scaling the power to ensure that we are, even though the collected sample have been higher than the center of the bin, we would just scale back to the center of the bin. And you can see here by looking at the standard deviation as function of the rank, that having between just the simple average or scaling the power help to reduce the variability for the first rank of turbines. And the second method that decrease even more the standard deviation or the uncertainty is the 2D bin interpolations. So in that case, we will bin the sample for each bin, and then we will do the interpolation at the center of the bin for the direction of wind speed and wind directions. So that's why we have a bit more complexity here. But those two methods suggest that having the same distribution in wind speed or having less noise by doing some interpolation help to reduce the variability. And then about the probability. So in the current process, we are using the long-term rainbows because we want to know the long-term impact of wake adapt in that specific wind farm. But at the beginning of the swap test, we will not cover the full rainbows, of course, but we will have only collected some few sectors. So we wanted to know what is the impact if we are changing this probability by only the probability based on the collected sample at each turbine, or if we do the same, but instead of looking at each turbine only based on the free stream turbines. And you can see that the standard deviation, so the variability or uncertainty, is decreasing when we are using the distribution based on the collected samples, and even more when we are doing based on at each turbine. The issue of the second one is that we have, due to the road check and the ensuring that all the upstream turbines are in operation, we have less samples at the downstream turbine than the free stream turbines. But the highest gain is at the downstream turbines, so it's a bit tricky to only use the probability based on the collected samples at each turbine. But if we use it based on the free stream turbines, it improves the variability, and especially at the beginning of the swap test. So this is the standard deviation as function of the time. And you can see that at the end, it doesn't really change anything. But during the first, 5 months, we have some smaller uncertainty when we are using the probability based on the collected samples. And then the last one, this one is based on the super reference turbines. So we have been explaining you that to ensure that we have some robust reference wind speed, we are selecting some super reference turbines. The issue is that by removing or by selecting those super reference turbines, we are reducing the estimated or potential gain of wake adapt. So we want to limit the number of super reference turbines. The issue is that you can see that if we are not restrictive to the maximum lateral distance, so basically if the super reference turbine is too far away from the turbine of interest, we might introduce some noise. because of the non-uniformity of the wind flow. So what I have tried here is to plot for different rank of turbines. So the first one is free stream turbine, first downstream, and so on. Different maximum lateral distance for defining the super reference turbines. And you can see that especially for the free stream turbines, the uncertainty is decreasing when we minimize the maximum lateral distance. The impact is less significant when we are going downstream, but at least it shows that if we are too far away for defining a super reference turbines, we are introducing also some variability inside the measured gain. And then this is the last one. So at the moment, we are just defining for one time step the reference conditions. But the issue is that the flow is not static, and we do have some flow propagation. So one of my colleagues is currently working on some models that account for the wind flow propagation to define reference conditions. So yeah, it is currently submitted for talk, but the main objective of this method is to use high frequency data only based on free stream turbines and include some time propagation to know when the reference wind speed and wind direction will be at the downstream turbines. And we have used this background flow to see if that would improve the uncertainty of this method. So basically in red you have without the propagation time, and in blue you have with the background flow and the propagation time. And you can see that especially for the downstream turbine, it helps to reduce the variability of the measured gain. And I'm running out of time, so just the last one about the conclusions. So I have tried to show you some method to evaluate the uncertainty of the to assess the wind farm control measured gain only by using some baseline datasets, so without any wake steering approaches. And from our, let's say, perspective, from the industrial perspective, it is kind of a challenge to have a robust method to measure the long-term benefit of wake steering without any external measurement, and if especially we want to have a quantification of the AP gain. And from the past investigation that I have just shared with you, the main blocking point is to quantify the AP gain and therefore to have some robust reference conditions that are within a very thin bin of the data. And I just wanted to conclude that it's much more complex to validate wind farm control than traditional power curve, because of wake propagation and non-uniform wind flow that needs to be accounted for. Yes, and if you have any question, we're happy to answer them.